I want to talk about a circuit which is, again, a resistive circuit with voltage sources and in particularly one voltage-dependent voltage source. And again, there's always a bit of stress that seems to happen as soon as people see voltage-dependent voltage sources. And so I want to kind of make sure that we kind of keep working through different examples, but these actually do have some strong meaning in terms of real circuits that we're going to build. In fact, some things we'll even see as we get further, might get further along in just even linear circuits. So you look at this structure and you go, okay, here is my dependent source. I have an input voltage and an output voltage here. So then the question is, how do I begin? Well, one of the things I can do is I can basically start writing KCL at different points. And I've got it at two nodes. One KCL at this node, which is just the current out of this resistor is the current into that resistor. That gives me these first two terms right here and here. And then then I say, well, then any current that's coming out through this resistor goes through this parallel combination of these two, which is both a load resistance and some sort of source resistance. Okay, so now we can ask all sorts of different questions there. In practice, you'll end up finding a lot of circuits where this RS is often 0. But before we do that, let's just take a look at how the circuit might be. And because if I'm looking at this particular equation here, I can actually do a pretty interesting simplification, or by just taking this and realizing, okay, let me take the a sub v part, and I can take, the terms all related to v. So pull all the v terms together. This gets pulled on the other side of that. Pull the v out over here. What happens is I get this expression of v equals to 1 over r2 minus a sub v over rs, and that equals to V out over this parallel combination of RS, R2, and RL. Now in general, RS is small. If you're going to build this kind of a system, typically RS is small. So I'm going to look at that particular case. And if RS is significantly smaller than R2 and RL, which is pretty typical to expect, and I have at least some sort of a little bit of A sub V that's a little bigger than 1, because we're going to typically talk about numbers in that size, then this whole thing here, the parallel combination, always goes to the smallest of the resistances. Well, in this case, that's just RS. In this case, if that's the smallest one, then even though this is negative, this is going to be the thing that's going to end up being the larger of the two. 1 over a small thing is a larger thing. And so what you find is, in the end, with this approximation, that basically end up getting that the output voltage is equal to minus times the gain times this particular voltage. Now, if RS was equal to 0, well, then this would go away. Then this voltage source is everything in that situation. And what I end up finding is then that V out would then just be equal to whatever this is. So I would just get that simple relationship. Cool, everything is good and consistent. So typically this is the way we would approach it. Now if you're curious, well, what happened if RS is much bigger, or this thing doesn't hold, this expression doesn't hold, it's an interesting example to kind of work your way through and see what it would do. But in practice, if you're going to probably build one of these structures, this is what you're going to see. Okay, so if this is the case, then that does reduce this part of the equation significantly. I still have this structure, but then I can substitute in for V two terms that give me a V out term. So that's what gives me this expression, which then I can collect terms, and I get V out with a whole bunch, 1 plus 1 over A sub V, whatever that term is, which often A sub V means kind of like a gain or a voltage gain, is then going to be equal to sort of this resistance ratio of R2 over R1. And so I can then write what is V out over V in, and we're going to kind of, we always get kind of used to this with linear circuits. We're going to see this often again and again as seeing these ratios, is R2 over R1 times a whole bunch of other elements in here. Well, in practice, what you might end up finding is you're going to build this into an amplifier where the gain is fairly high. So let's take a typical set of numbers. Maybe this is going to drive a 1 kilo ohm load. Of course, it doesn't really matter. It doesn't show up in the numbers here. A gain of maybe 100,000, which is a pretty typical number. And R1 and R2 are 10 and 100K, typical numbers you'd find with discrete elements in a lab. And what you'd find is that R2 over R1, this is 10, right? And so that'd be minus 10. And so this entire thing turns out to be a small correction factor. If you calculate it out as 0.999, that's pretty close to -10, and so it's really, really close to this, and kind of typically why we often will use an amplifier structure so I can actually get a nice, precise result based on these two resistors. Works well. We will actually see these kinds of things in other kinds of circuits in different places, and part of that would be something like what you'd see for this op-amp circuit, where I have an op-amp here with two resistors R1 and R2 around it. This structure basically is meant to be a voltage-controlled voltage source. So it would be modeled very simply by this kind of an element. And it would probably be driving some resistive load. And the way you would look at this circuit and analyze it, you would expect a sort of voltage gain that's going to be R2 or R1, and that it'll be inverting. And so these sort of things, allow you to kind of see where these kind of analyses are. Even more, if you get used to looking at this kind of circuit, there's some tricks to getting that answer very quickly. But if you say, well, what happens if my gain isn't like super high? What in my correction terms would look like? Well, I can always go back and reanalyze it in a very straightforward way.